Today's lesson will be 11.1 sequences. There are two types of sequences that we're going to be talking about today. The first one is an infinite sequence, which is a function whose domain is the set of natural numbers. And it's infinite because it continues on forever. So you see by the continuation right there that it will have no ending. So infinite means it continues on if it's an infinite sequence. The other type of sequence is a finite sequence, which is a function whose domain is the set of natural numbers. And you can see by this example that it ends at a certain number, okay, where n is a natural number in which it ends. When we're given a sequence, we see that each number is a term of the sequence. So if we go back up to the example in the finite, the number 3 would be a term of that sequence, as would the number 4 would be a term of that as well. Now, n right there would denote a general sequence. So if we say the nth term, that would be a general sequence, or a general term of that. If we take a look at this first one, usually how sequences are written is kind of in this format. You see how it says a sub n equals, and then it kind of gives you the formula of which it follows. N itself being, again, that general term, and you can do each of those terms by kind of following out. So we do a sub 1, a sub 2, a sub 3, a sub 4, a of 5. And basically, so what we're going to do is we're going to take the 1 in this case, and it substitutes in for the notation n, or that variable n. So what you're going to get is you're going to get 10 minus 1 squared, which would be 9. So we'd say the first term in the sequence would be 9. Then we'd follow that pattern. We'd do 10 minus 2 squared, and that would be 10 minus 4, which would be 6. So 6 would be the next term. And then 10 minus 3 squared, which would be 1. It would be the third term, and you keep going. So 10 minus 4 squared, that would be negative 6. And 10 minus 5 squared, which would equal negative 15. Now you can always follow that pattern and find each subsequent term of the pattern, so the first, second, third, fourth, or else you can just skip around depending on what you need. So if we look at this one, and I'm looking for the first term, we're going to start at the beginning. We plug in the first number, so 1 for n, and we plug in for every time we see n. So it's negative 1 to the first power, then it's 2 times 1. So that's going to be negative 1 over 2, which is negative 1/2. But when we get to b, you notice that we're trying to find the sixth term. So we're going to plug in 6 to find out what that term will be. So negative 1 to the 6th power is positive 1. And that's going to be over 12. So the sixth term would be 1/12. And then we can keep going when we do c. The 50th term. So we're going to do a to 50. So you don't necessarily need every single number up until 50. We can just go ahead and plug in for 50. So negative 1 to the 50 power, and then 2 times 50. So that's going to give us 1 over 100 for the 50th term. And finally, d, we're going to plug in 17. So we're going to get negative 1 to the 17th power, and that's over 2 times 17. Will give you negative 1 over 34. Now what you're also going to be asked to do is, once you are given part of a sequence, is to find out the general pattern, or the general term of the sequence. So some patterns are going to be a lot more obvious than others, while others are a little bit more difficult. Now if you can figure out that pattern right away, you can just go ahead and write that pattern. But in some cases, it might be helpful to kind of match it up and see what happens with each one. So the first term is 1, the first term is 8, the third term is 27, and then the fourth term is 64. And you just want to kind of see, is there a relationship between the 2 and the 8, the 1 and the 1, the 3 and the 27, the 4 and the 64. And the 1 to the 1 doesn't really show us much. But if you kind of think about how you can get from 2 to 8 and 3 to 27, what happens is that we're going to be taking that number and we're going to be cubing it. So the general term for this would be a sub n equals n to the third power. Why don't you pause the video and see if you can come up with the patterns for the next 3. Alright, so I started by kind of laying out all the terms and matching them together. If you take a look at the first one, what happens is you're going to take the term and you're multiplying it by 5 each time. So in this case, the general term would be a sub n equals 5n, because you times the term by the number 5. For C, if you kind of notice, again, the first one doesn't really help. If we look at the pattern going from 2 to 1/4, 3 to 1/9, and 4 to 1/16, you're basically taking 1 over the term squared. And finally, with D, you'll notice that what you're doing from each one is you're multiplying it by -2. So we're going to take each term, the number of the term, multiply it by -2. And finally, we're going to take a look at a word problem to kind of show how it can be used and applied. And it's very similar. It's just kind of using it in terms of a real-life example. A certain strain of bacteria grows according to the sequence a sub n equals 100 times quantity 2 to the nth power, where n is the number of hour just beginning, and a sub n is the size of the culture. Find the size of the culture at the beginning of the 5th hour. So basically, we know the term that we're looking for is the 5th. So it's the beginning of that. So it's the 5th hour. So we're going to find the 5th term, basically. So a sub 5 equals 100 times 2 to the 5th power. 2 to the 5th power is 32. 100 times 32 is 3,200. So it would be 3,200 bacteria.